Okay, Assalamualaikum warahmatullahi wabarakatuh. To all of you, sorry uh, I was not able to upload the video yesterday because I was really busy in completing the monograph. eh. I'm actually in the process of improving the notes that we have and put it, consolidate it, and make it as a monograph or a book as a reference for the power electronics course EPO510. So before we proceed with the lecture, I would like to give some review, refresh back what we did before the MCO or the PKP. Okay, so the course outcome of the power electronics is at the end of the course, students should be able to describe the characteristic of power switching devices and the drive requirements, which is actually covered by topic number 2, whereby we discuss on the characteristic of power switching. These are the type of switching devices. We have a uncontrolled control device. Then we have thyristors, diodes. So the topic number 2 or topic number 1 actually covered the course outcome number 1, and then the rest is actually number 2, to evaluate the operation of power electronic converter circuits. Okay, and finally the outcomes is after you complete this power electronics course, you will be able to simulate various converter circuit topologies and control strategies. So in this case, for EPO510 in my class, I usually use PSIM. I hope by now everybody has installed the PSIM version 11 that I did share with you through the Padlet. Please use that version because I found out that the latest version is quite difficult to handle. Right? So install it from time to time. Please make sure you use it and start with a simple circuit before you go to more complicated circuits. Right? So this mainly the course outcome of the power electronics. Okay, because due to the MCO, the PKP, we have revised the lesson plan, and now I also shared this lesson plan, the new lesson plan in the Padlet. So please make sure you download yours, and let's have a look what we have in this lesson plan. Okay, so we have done I think we completed before PKP, we completed about 4 weeks, right? So first week, second week, we discussed on the introduction of power electronics, characteristic of the introduction of power electronics, and then we move into AC/DC, right? And just after the MCO, I think we have covered the single phase half wave rectifier and covering the inductive load, right? R plus L, and then we have this extinction angle. I hope everybody still remember that, right? We have this extinction angle, and then we try to calculate the beta using the calculator, the shifts of things, right? And the rest. Okay, and then now for lecture week number 5, we're going to continue with single phase half wave rectifier, complete the topics, and then we move on to the full wave rectifier. Again, we're going to describe the principal operation and with the analysis of resistive load, inductive load, and the rest. Okay, so that will be covered in week 5 and week 6. Still, you have a single phase uncontrolled rectifiers, and then we're going to complete the single phase control rectifiers, which we're going to use the thyristors. For control rectifier, we're going to utilize the thyristors, and then up to week 7. For week 8, we're going to start with a 3-phase. I think I can do we can start earlier than the week number 8. Okay, inshallah. And then we're going to have our first test, which is online open book test. Again, I hope you do it is based on integrity. Don't copy your friends, don't discuss with your friend. It's an open book. You don't have to discuss, you just open book, get the answers by yourself, and then it's going to be done through quizzes. There is a software or apps which is known as quizzes. We're going to use that platform to evaluate your test on, and that will be on the 6th May. That will be on the 6th May 2020. And then next 3 phase, we're going to continue the week 9, and after that complete the rectifiers. We move on to the AC voltage controllers, and then we're going to have a special break for the Raya for 1 week, and then we come back. We continue with the DC choppers week 11, week 12, and then finally inverters in week 13, and then we're going to have another test 2 on the 24th of June 2020, and we have another week left after the test, and then we're going to have a group assignments. Okay, for the group assignments, we're going to have 3 or 4 members a group, and you'll be having individual questions. Each of the group will have a different questions, and then you will do the simulation, right, for the inverter simulation, and then you must compare with the theory. And there will be a 20-minute live presentations, which means every group will be online, or we're going to have probably we're going to use a Zoom or WebEx platform, and then you're going to present to me the outcomes of your group assignments. So everybody have to talk, everybody have to present, and that will give you the marks for your group assignment. So because of this PKP, the assessment will be different. There will be 15% for test 1, 50% for test 2, and then the group assignment will be 10%, and the final test is maintained at 60%. So the final test there will be a timetable, which means the faculty will choose one date for us for the power electronics, and they'll be through online again, right? Inshallah, we try to look into the probably multiple choice type of questions, and also other platform that we can use. Okay, so that makes up your 100%. So again, this is 100% online or ODL. Now the term is ODL, which means open and distant learning. So I hope everybody can try to get the maximum internet connections. So that's why I use the Facebook as a medium, as a platform for the lecture, because I believe everybody has the Facebook, and we have also the unlimited data for Facebook. So make full use of the Facebook facility. I don't want to go for Zooms or the WebEx, face-to-face, I mean the online real-time lecture, because that will limit the lectures, because some of you may have a poor connection of internet. So we're going to use a Facebook as a medium of the lecture, and I hope everybody has a good time, inshallah. I also like to come back to this Bloom's taxonomy. This is very important, because as you move on, as you start to learn new things, you have to always check yourself, the level of understanding, the level of your brain, your current states of understanding. You are at this knowledge level, the first level, or remembering, you just remember anything. Okay, and then you have a second level, which is understanding, comprehensions. If you are at this level, you can explain the operations, okay, rather than you just memorize the name of the rectifier. So this is the comprehension or understanding level. And then you move into the level number 3, which is applying applications, whereby you can solve problems to new situation by applying acquired knowledge. Once you understand, then you can apply your understanding in solving the problems. And then analyzing, whereby after you have these 3 levels, then you can examine and break information into parts of understanding motives, causes, make inferences, and find evidence to support generalization. So you can analyze. After that, you have this evaluating level, whereby you can present and defend opinions, making judgment, variety of ideas, and finally you have this creating level. Okay, so this is the Bloom's taxonomy. So always check yourself, where are you now? You understand the contents of the lecture? Can you apply to solve the problems? Can you analyze and give some power factor, for example, the performance parameters? You can derive equations. And then evaluating is actually where you come into stage of designing, so on and so forth. Okay, creating. Right. So there is a verbs for each Bloom's level, Bloom's taxonomy level. And this is the verbs according to the stage. Okay, so always check and always use this Bloom's taxonomy action verbs. Okay, so now I would like to go to the monograph that I finally have time to complete, not to half done actually. I'm going to give you the complete monograph, the complete books after I finish all the notes. Okay, so Alhamdulillah, with this PKP, I have time to complete the notes, complete the monograph, and I think that will help you during the next time. Okay, for chapter 1, again, there's an introduction to power electronics. What is a power electronics? So the definition of power electronics, a field of electrical engineering that deals with the application for the control and conversion electric power by supplying voltage and current in form that is optimally suited for user load. So you have an input and then the output, and it can be the form of AC to DC, and the output also can be the form of AC to DC, and therefore we need these power electronic converters, which will be covered by EPO510. So we have AC to AC, or again we start with AC to DC, and then we have AC to AC, and we have DC to DC, and finally DC to AC. For a complete system, we need to have this controller, right? So that we can regulate, we can control the output voltage, because normally load requires a stable input voltage to the load. So the power electronic converters must have a control so that it will stabilize the output or the input voltage for the load. Okay, so to obtain that regulated output, we need to have this closed loop circuit, whereby you have the sensors and then the feedback system here. You have a controller to change the duty ratio. You can change the frequency so that it change the output voltage and therefore maintaining the load. Okay, and then the goal of electronic converters, I always emphasize on the goal of electronic power conversion, whereby while doing this conversion, we need to make sure that it is the highest efficiency, high availability, high reliability, lowest cost, small size, and weight. Okay, and then we have this conversion concept. Hope I don't have to go through this again, right? So in your book, actually, we have this document map on the left hand side here, so you can browse through straight away to the chapter if you like. So this is chapter number 2. I put on an extra note on the review of basic electrical concept. And here put a notations. This is the notations that we're going to use throughout the books, throughout the lecture. Right? The capital V, the small letter will be the instantaneous voltage. The capital letter will be the RMS. If you have a look at this we have this V of hat. there's a hat above the V, so that means it is a peak value. And for the three phase later on, there will be a phase voltage as well as the line to line voltage. RMS of the phase voltage, RMS of the line to line voltage, and we have also the peak of the phase voltage, peak of the line to line voltage. So make sure that you look into these notations. And then and also I add the waveform, how to sketch the waveform, because when we deal the three-phase rectifier later on, we need to sketch the waveform, right? So there is a technique for you to draw it correctly. So I put on here the techniques, the steps for you to get the proper sine wave for the three-phase system. So the first one would be a three-phase supply voltage. It is a phase voltage, and then look at that, and then we have this three-phase supply line to line voltage. Remember, we have phase voltage and also line to line voltage. So this is how the technique for you to sketch a proper line to line voltage. Look at that, and this will be the final line to line voltage. So you have to follow the steps so that you get a proper pulse durations. For example, in this line to line voltage, the duration between the pulse is 60 degree. It is always 60 degree across that. So if you don't follow the steps, you have the same waveform, but then the pulse is no longer 60 degree, right? Okay, so you just follow whatever you have here, then you get the nice 6 pulse, the line to line voltage. And before the break, we go through the Fourier's theorem. I hope you still remember. The Fourier actually says that any waveform is actually a combination of sinusoidal, individual sinusoidal voltage waveform at different frequency with different amplitude, isn't it? So I put it this on the review of basic electrical concepts here. So go through again. Now you have I put it in the equations. Okay, so easy to follow. So in this equation we have this is the Fourier series equation. F of t, all the waveform can be described by, at first we have the A0 over 2. So this A0 over 2 actually represent the DC component, the average value. This is the average value. And then we have another components which made of AN, coefficient of AN and BN, and that will lead to CN here. If you know what is a BN and AN, then finally you can find what is a CN. And normally the Fourier series representation or Fourier series is actually written in the form of Cn sine n omega t plus Vn. So Alhamdulillah, before the break we did before the MCO we did look into the Fourier series. Of course, the first time you look in very difficult equation, but as you practice, try to use it again and again, inshallah you are going to memorize that. And this is Cn coefficient Vn, and we look into the example. I provide you an example here. So this waveform actually generated using the PSIM. Okay, this is obtained through PSIM, and the equation for that, the Fourier series representation of this waveform is actually in the form of 10 plus and the rest. So which means this waveform actually made of a DC component of 10 volts, and then we have this 50 Hz frequency because it's omega t. The amplitude is 25. Sorry. And then you have the third components which is at 150 Hz. The component is the amplitude is 8 volt, and followed by fifth components, seventh components, and ninth component. If you add this the equations, then you get this waveform. Okay, right. I think I have to. Okay, right. So that equation also can be represented by this harmonic spectrum, whereby the first component here, remember, is a 10 volt. So it is located at, sorry, it is located at 0 hertz. So 0 hertz is a DC component, and then we have 50 hertz, 150 hertz, 250, 350, and 450. So in harmonic spectrum, you're going to see these components displayed or given to you. Okay? So this is a harmonic spectrum, and that equation also can be represented by individual waveforms as this. So we have DC components at 10 volt, right? And then the first 50 hertz component, which is at 25 volt amplitude. So if you measure, this will be a, if you measure, then you get a 25 volt amplitude, and then this is 8 volt for 3 hertz, for third harmonics, which is 150 hertz. So it's sorry, so it's 3 times faster than the 50 hertz, and then we have 5 times faster than 50 hertz, and the rest. So this is a Fourier theorems for the power tree. It's very, very important for power tree that you understand the Fourier series. And because of that, then to carry out the Fourier analysis, we also need to look into the symmetry of the waveforms. Okay, once you once the waveform symmetry is identified, then it will simplify. I always use the simplify. So this is actually to ease the analysis, to help you in analysis, because remember you have an to evaluate, bn to evaluate, and you have the whole period 0 to t to evaluate. Therefore, if you know the symmetry of the waveform, you can use the properties of the symmetry, whereby sometimes you don't have to find the an, sometimes you don't have to bn, and you can also have some properties. For example, n is odd, n is even, and so that will simplify your analysis. So go through again, refresh yourself for the Fourier analysis. I also provide this table for you, and the first in do the analysis, we look into the Fourier series of a square waveform. This square waveform, again, we're going to deal with this square waveform again when we discuss on the single phase full wave rectifier with a highly inductive load. Right? So therefore, I started with this Fourier series of a square waveform. So again, Fourier says that any waveform can be represented by a series of combination of sinusoidal signals at different frequency with different amplitude, plus if there is a DC component. Okay, for this square waveform, if you have a quick look, there is no DC component, isn't it? Because the positive area, this is a positive area, equals to the negative area here. Okay, there are identical areas, so you don't have the average of the square waveform. And then if you go through the symmetry, the waveform is actually odd and half wave symmetry, and therefore the square waveform also a quarter wave, odd and quarter wave symmetry. So refer to the table 2.1 just now, then you will get, if you go back to the table 2.1, you're going to see for odd and quarter wave, an is 0. Okay, an is 0, so you don't have to evaluate for an, just leave the an. We focus on the bn. But the for even harmonics, even n, bn is 0. So the bn here only exists for odd n. Okay, 1, 3, 5, 7. it's possibility that this will be exist for 1, 3, 5, 7 on the odd numbers. So just use this equation, we evaluate that. So I'm going to use this equation to evaluate the square waveform. So this is square waveform. So from the table, an is 0 and the rest. Okay, just read that, and then you focus on solving the Bn. It's very simple. It's a constant IDC. So if you evaluate, if you integrate a constant, you get then only the x. By the way, okay. So finally, you found out that for the square waveform, it exists for the 1, 3, 5, 7, the odd harmonics, and the amplitude of the waveform, the Bn or Cn, is equals to 4IDC over n pi. So Cn is always positive. If you look at this equation, okay, if you look at this equation, Cn is always positive, and that's why if you look at the harmonic spectrum, it is always represented by this bar, isn't it? It's always a positive value for the harmonic spectrum. So that actually because of this Cn is positive because of that modulus. Okay, absolute value. Right, so I is equals to 4 IDC over n pi sine n omega t. So again 1357. So the equation, the Fourier series for the square waveform is 4 IDC over pi, 4 IDC over 3 pi. And look at the sign, the individual sign, sine 3 omega t, sine 5 omega t, 7 omega t. So this is the equation, and if in terms of harmonic spectrum, this is what you're going to obtain for square waveform. The fundamental, the third, the fifth, the seventh, the ninth harmonics. Okay, and then we also need to look at the RMS of the fundamental. So I show you the RMS of the S1 as well as the ninth harmonic. So if you look IS1 as well as this is the RMS of the fundamental. So to get the RMS of the first component, you just divide by square root 2. Whatever the peak amplitude here, divide by square root 2, because this is actually the sinusoidal signal, isn't it? So the RMS is only divided by square root 2. So that gives you the RMS of the fundamental component. Okay, question 2.14. Right, so we also look into the RMS of the total current, which is the square waveform itself. What will be the RMS? So I will also show here how to obtain the RMS. This is the general equation. So always memorize this. To get the RMS, you have to square root, and then this is the average. Root mean square. Remember, we have root mean square. So you just draw the root and then draw the mean equation and then square that mean equation. That will give you the RMS of any waveforms. Okay, so solve that, you get the RMS of a square waveform equals to IDC, the amplitude of the constant current. Okay, and then we move into the power and power factor. I explained here the power factor concept. So please look again the actual definition of a power factor, right? The true definition of power factor. Okay, so I show you here what is a power factor for a non-sinusoidal current, and this is a non-sinusoidal current, and now we have a sinusoidal current, and that's why for a sinusoidal current, before this you always define power factor as cos theta, isn't it? So if you follow this note, you will understand why power factor is always cos theta for a sinusoidal and current and voltage. Okay, and then we move on into, I don't think I want to go back to this overview of power. So we also touch on the overview of power semiconductor devices. in here, look at this. Okay, so we've covered all of this. I just want to focus on just give a refreshment on the power switch losses. So just click here, goes to power switch losses. Okay, it's important to consider losses of power switches. Then we have three types of losses: forward conduction losses, and then we have blocking state losses, and finally the switching losses. So this is the theory behind the switching losses, and then include the derivation of average switching power losses, and finally some calculation to show you the example of the power switching, the average of the power switching losses. Right, and then we start with the single phase uncontrolled rectifier. We've started with the single phase half wave rectifier. So to explain the operations, we always start with refer the supply voltage. So we have a positive half cycle here. This is known as a positive half cycle, and this is the negative half cycle. Yeah, positive half cycle, negative half cycle. So you also need to understand that the diode operates depending on the voltage and current of the circuit. It will only turn on when the voltage is forward bias, and we have the current that follow through the current that flows in the same direction of the diode symbol here, right? So that will turn on the diode. Okay, so for single phase half wave control rectifier, look at the positive half cycle. Okay, and because of that positive half cycle, diode experience the forward bias, and because this is a resistor, so the current start to flow clockwise, and therefore diode is on. So whenever diode is on, it will appear as a short circuit. Okay, it will appear as a short circuit, therefore connecting VDC to VS. So therefore output voltage we always refer to, equals to the supply voltage, and that's why the VDC here will copy the supply voltage here. It will just copy the supply voltage. And during negative half cycle, okay, during negative half cycle, the diode will be reverse bias, and the current start to flow in the opposite direction, anti-clockwise, because this is a resistor, so current start to flow, but then because this is a reverse bias, then diode will be turned off, so it will appear as a open circuit. Therefore there is no current flow, therefore the voltage drop across R will be 0, and that's why for the negative half cycle you're going to see that the current the voltage is 0. Okay, so just to give you some refreshment, and then we will always look into the average output voltage. So okay, always memorize the general equation. So to get the average value, you must integrate from 0 to t, the whole cycles, the function of the waveforms, and then you have to divide by t, yeah, the total period, one cycle. And then it's convenient for you to change to radian, therefore one cycle equals 2 pi, 0 to 2 pi VDC theta d theta, and then you get this equation, yeah, for output voltage and the rest. I hope you go back and go through this again, and please, I think I've shared with you through Padlet the PSIM circuit. So try to beat yourself, try to construct the circuit through PSIM yourself, and then just refer back to and just make a comparison with the one that I shared with you. So you must construct the circuit through PSIM yourself, right? And then you can validate, you can verify the theoretical answer or the theoretical results from the equations that you have just now to verify your answers. Okay, then you have problem 1, problem 2. So again, look at this. You have calculate. This is actually to, when we have this sort of questions, then you know that you must perform the harmonic, the Fourier series. So try yourself, try to get the Fourier harmonics, to get the harmonics of this waveform by using the Fourier analysis that we did just now. Based on the square waveform, try to when you understand that the steps, then you can apply here. So if you look at this waveform, I don't think it is a odd waveform. It is not even waveform. It is not odd waveform, and it is also not the half wave symmetry. So you have to perform as a normal function, an, bn, integrate. Inshallah, you will get this answer, right? Answers, and compare with your PC. Okay, and then we go to the performance parameters. So look back. All this power factor, displacement factor, and the form factor. These two also important. Form factor as well as the ripple factor. This is less important. Distortion factor is important. Displacement factor is important, whereby the power factor, the actual power factor equation is actually this one. Okay, IS1 over IS cos B1 cos B1. The THD, total harmonic distortion, and the harmonics. So if you don't know the waveform, if you are given in terms of individual harmonics, you can find the RMS of the components by using this equation. Or else, if you are provided with the waveform and you can evaluate the waveform, the RMS can be actually it is more accurate if you use the equation, the root mean square just now. Okay, let's proceed. And then we look into resistive and inductive load, whereby for resistive inductive load, you have a beta extinction angle. You still remember that extinction angle? So for this circuit, you have to remember we have this energy elements here stored, the inductor. So inductor actually, their behavior is the characteristic is stored some energy, and the current cannot change the direction instantaneously, okay, because of that stored energy. So therefore, just to refresh again, so during positive half cycle, right, so during the positive half cycle, the current will start to flow in this direction, and the voltage also forward bias, and therefore VDC equals to Vs. Sorry. So if you look at this waveform, VDC will copy the Vs, but only up to that point. Okay. When it crosses the negative into negative half cycles, the diode here actually reverse bias, because it's a negative voltage rate. But due to the current, if you look at further, the current is still flowing in this direction. In that direction, isn't it? The current is still flowing in that direction because you have the stored energy in your inductor. Therefore, it will causes the diode to stay on. It will remain turned on until this current is 0. Okay, so that's why if you look at this waveform, the currents, the voltage still copy the negative here. It still copy the negative area here until current equals to 0 at extinction angle. So when the current is 0, the diode will be open circuit, turn off open circuits, and therefore voltage equals to 0 again. Be 0 again. Okay, so that is your waveform. So of course you're going to get a different output voltage, average, as well as the RMS. I hope I must emphasis on you complete the gap here. There is a missing solution calculations here, so please make sure that you fill in the gaps. Right? Don't just memorize the equation. So fill in the gaps. So the average output voltage will be that, and okay. And for the equations, I put here the detail on how to obtain the equation for the current. So you have a forced response circuit, the natural response circuit. Please go through. Inshallah, you'll be understand how it derived. And finally, you have this equation. In terms of theta, you have I theta equals to V peak over Z sine theta minus V plus V peak Z over Z sine V. So you use the equation and put in the value of theta and everything, so you can find, you can look for your beta when you set this equation equals to 0. And please use the PCM again to verify the equation. I'm not sure whether we have started the resistive inductive back EMF. Okay, I think we stop at this particular point. Then we're going to continue with the next video. I think we stopped at before the back EMF 4.2.4. So next video will be continue. We're going to continue the lecture notes as for week after the actual lecture, after the break, after the MPKP. Okay, take a break and then we come back with a new video on the resistive inductive back EMF. Thank you.